How do you analyze complex electrical faults in power systems? Imagine trying to find a tiny leak in a giant water pipe system. That's similar to analyzing complex electrical faults in power systems. It's a step-by-step process that keeps the lights on and equipment safe. When a fault happens, it can be symmetrical or unsymmetrical. Symmetrical faults are balanced, like a three-phase short circuit, while unsymmetrical faults are imbalanced, such as a single line-to-ground fault. These are more common and trickier to analyze. To handle unsymmetrical faults, engineers use a method called the symmetrical components technique. This method breaks down imbalanced signals into three parts: positive sequence, negative sequence, and zero sequence components. Think of it as splitting a complex problem into three simpler ones. First, you model the system components like transmission lines, generators, and transformers by their sequence impedances. These impedances are like resistance and reactance values that tell you how each part responds to faults. Next, you build separate sequence networks for zero, positive, and negative sequences based on these impedance values. Then, depending on the fault type, you connect these networks in specific ways. For example, a single line-to-ground fault connects all three networks in series, while a line-to-line fault connects only the positive and negative networks. Once connected, you analyze these networks using basic circuit analysis techniques to find the sequence voltages and currents. After that, you convert these sequence quantities back into phase quantities using a mathematical transformation. This step gives you the actual fault currents and voltages at the fault location. Knowing the magnitude and direction of these currents is essential for setting protective devices like relays and circuit breakers. These devices are designed to trip and isolate faults quickly, preventing damage. In real-world power distribution and renewable energy systems, this analysis helps in designing relay protection schemes that respond accurately to different faults. It also ensures that switchgear and circuit breakers can safely interrupt high fault currents. Grounding methods, such as solid grounding or resistance grounding, influence the fault current levels, so understanding these helps in proper system design. Engineers often use computer tools like MATLAB or specialized power system software to simulate faults and automate calculations. When doing these analyses, engineers usually ignore per-fault load currents to simplify the process and assume the system was balanced before the fault. They also model non-rotating loads as negligible and consider the effects of fault impedance, which can reduce fault currents. This structured approach allows for precise fault analysis, which is vital for reliable power system operation and protection. It ensures that faults are quickly identified and cleared, keeping the power flowing smoothly and safely.